Right, here we've got a 2011 paper, for light and materials. Straight away I can see bright and dark spots, so we're talking about a double slit experiment. Alright, the first question is calculate the path difference from between slit 1 and P and slit 2 and P, so path difference to P basically. So the path difference in this case is, you always count out, so this is 0.5 of a wavelength. The next white one, because C is the centre. We've got the centre of the pattern C. I'm just going to, jump back here. We've got the wavelength lambda. They've given us the separation, but we don't need to use that. Counting out from the middle, half a wavelength. One wavelength to the next bright spot. 1.5 wavelengths path difference to point P. So the path difference at that point equals 1.5 wavelengths, which equals 1.5 times, and the wavelength is 560 nanometers. So 1.5 times 560 is 840 nanometers. Alright, they now increase L. So they make the make this further away. Describe the effect of the change on the spacing of the observed bright interference patterns. So we did this one in class when we had our diffraction grating. As you move the laser and the diffraction grating further away from the wall, the bright spots get further apart. So we could just say bright spots get further apart. That's only worth one mark. Next page of this, it says L set to its original value, and now the separation of the slits D is decreased. So they've gone from the two slits maybe looking like this, so this two slits getting much closer together. Describe the effect of this change on the spacing of the observed interference pattern. Now these, and same with the last question as well, so maybe something you want to have on your cheat sheet. What happens as we change the wavelength, as we change the frequency, as we change the length, as we change the distance between slits. As the slits get closer together, it turns out the fringes or the bright spots get further apart again. Bright spots get further apart. And this is worth 2 marks, so I'm going to put an answer, a reason as well. That's my first of what happens and why that's the case. And it's because as the slits get closer together, as slits get closer, we need to go further from the center of the screen where we're looking at the bright spots and the dark spots, to get path differences, PD, path differences of full wavelength. Because these are so close together, it's going to be harder to get, to go further out on the screen over here, from the middle, way out over here, to get a considerable path difference, the difference in the length from here to here, and the difference from the length from here to here. As opposed to, say, over here, look at that, such a huge difference because the slits are so big. And remember, path difference is equal to the number of, when you get it equal to a whole number of wavelengths, you get bright spots. So because as the slits get closer, we need to go further from the center of the screen to get path differences of full wavelengths, which are bright spots. Alright. Explain how the observations in Young's double slit experiment led to his conclusions about the wave-like nature of light. 3 marks, 3 dot points. So Young observed interference, he observed bright and dark fringes. Now this can only be explained by constructive and destructive interference of waves. Therefore, light has wave properties.